Okay, this is like the third time I've done this video, so I'm really ready to get it over with. I know it looks weird. Okay. Fatty acids, long, unbranched hydrocarbons with a carboxylic acid group at one end. This should be review for everyone who was there on Friday. The reason that we're talking about it again is because saturated and unsaturated. If you don't know what that is, this is going to be a long lecture. So, if you do not have double bonds, you are saturated. If you do have double bonds, you are unsaturated. Let me show you what that looks like. You are saturated with hydrogens, basically. As many hydrogens as are possible, you have those. Unsaturated means that this one does not have as many hydrogens as possible, so it's unsaturated. It is monounsaturated because it only has one double bond. Polyunsaturated, it has two double bonds, or more than one double bond, and it does not have as many hydrogens as possible. So polyunsaturated have more than one. And they look like this. These that are saturated, they line up really nicely like this, and they are solids. These guys here are kinky here, and so because of these little kinks, they don't line up together, and they're usually liquids or oils. And that's what that looks like. Animal fats are typically solid, whereas vegetables are oils or liquid, but their structure looks the same, they just have those double bonds. A saturated the hydrocarbon chain in saturated acids are uniform and they nestle together again, and they look like this. This looks like fat, this looks like an oil. Unsaturated acids, this guy has a kink. They contain cis. I'm not going to ask you the cis and the trans. Just chill out about that. Don't worry about it. The kinks make it difficult for them to nestle together, and therefore it is harder for them to solidify. The primary function of tricycloglycerols is energy. Okay, so where are we? We are already, we are right at the end of this page here. Well, you can't see it. Right at where we're talking about triglycerides. So now we are moving on to adipose tissue. So you can see in your notes, I can't draw. Well, I can't draw, and I don't have the capacity to draw on this computer quite yet. Basically, if we go back up here, you want to know that there's a glycerol. Imagine that I'm writing a glycerol here, and then somehow there's 1, 2, 3 fatty acids. That's in your notes. You need to circle that. You need to find the place it's under triglycerides where it just has glycerol and then 3 fatty acids. You need to know that because we will talk about it later. Now move on to adipose tissue. So if we go back up here, the long-term storage is energy. Below that it says adipose tissue serves to provide thermal insulation and protective padding. It's always nice to say nice things about your adipose tissue. Just FYI, oxidation causes rancidity, decomposition, and unpleasant odors. So when fat starts to go rancid, that's actually an oxidation reaction. Don't panic about that. It's just like FYI, for your information, that's free. You can just put free. I don't have to know for the test. I just wanted you to know. Okay. A little review. This is important. This is going to show up later. Fat. It's nonpolar. It's hydrophobic. This is so awesome. When we go through all the processes by which the lumen digests in your intestines, all this stuff, then you're going to be like, oh my gosh, I love fat so much because it just goes right through that phospholipid bilayer. It's awesome. And we did it on Friday, and I think we did it on Wednesday too. I feel like we've done it twice. We did it Friday and then we did some more on Monday. Basically, it just goes right through. I'll draw that for you again. There's no ionic charges, so it just right through, right through. It's like magic. So fats, solid fats, have a high proportion of saturated fatty acid chains, so they just lay really nicely. And liquids or oils have a high proportion of unsaturated. Hydrogenation. So skip some stuff. Oh no, we're not skipping stuff. We're going right to hydrogenation. Hold on to the skipping because we're doing hydrogenation. Okay, I forgot about that. That was right next. Focus. Okay, hydrogenation. Dude, you can just, so everybody thought, hey, you know what? Oh, animal fat is bad. That's bad for you. You can have high cholesterol and get a heart attack. So they decided to just, all right, let's saturate and unsaturate things. So we can make things saturated if you want to. So for example, margarine. It's easy to cut. It's so fun to make cookies, right? You have the little stick and you cut it. That's great. So what we've done is we've taken something that actually is historically unsaturated and has little bonds, and we just hydrogenated it, right? We just add hydrogen. That's the whole thing. And what is it saturated with? It's saturated with hydrogen. If you want it to be saturated, you just add more hydrogen. Easy peasy. That's exactly what hydrogenation does. It just adds. Boom. Up here, look at that. Oh, this makes us unsaturated. This makes kinks. This is terrible. We want it to be a solid so we can put it in sticks so people can make cookies. Boom, hydrogens. You just hydrogenate that thing. It's not actually that easy. I'm not asking you for the chemical reaction. I'm just telling you that hydrogenation is adding hydrogens. It's easier to remember than all the G words. Hydrolysis. So also tricycloglycerols can be hydrolyzed in the body. So basically this hydrolysis is catalyzed by hydrolase. Don't you love that enzymes have such great names that tell you exactly what they do? Hydrolase, hydrolysis. Basically, it hydrolyzes the proteins, and this is the first reaction in the digestion of fats. Let's talk about bile. Yes. Okay. So we have hydrolyzed things and we have broken them down. Now's the point where you're going to skip like 3 pages. You're skipping glycoproteins, you're skipping sterols, you're skipping cholesterol, you're skipping all that. And you're going straight to bile. Because that's awesome. Because we weren't going to talk about some bile. Bile are essential for the emulsification of fats. So we've broken them down a little bit, but dude, you need the bile. So where does this happen? So the bile, this is synthesized in the liver. This is confusing. It's synthesized in the liver. Bile, synthesized in the liver from cholesterol, and it's stored in the gallbladder. So if you have to have your gallbladder removed, you're not going to die. It just, you can't eat a ton of fat at once. So if you have had your gallbladder removed, it's best to not drink a cup of fat. If you do, it will bad things will happen. Bad things will happen to you even if you have a gallbladder and you eat a cup of fat. But focus. This happens in the liver and it's stored in the gallbladder. So it's just storage for like if you need a whole bunch of bile to emulsify your fat. But you can survive without a gallbladder. Lots and lots of people do. These molecules have a polar end and a nonpolar end. What else have we done? And it smelled nice, and some of you added glitter to it. Soap, yes, same reaction. I swear, I don't make you do things in lab that have no purpose. And that soap, it's exactly like bile, except it smells nice and you can add glitter to it, and I wouldn't do any of that with bile. It creates the micelles. Do you remember the micelles? Yes. Remember the little polar heads get in there and are like, hey, come on, fat, let's go. We got some stuff to do. We gotta make energy. Micelles. That's exactly what the bile is doing. They're essential for the digestion of fat. Basically, it's awesome, right? I will have pictures later of it, but trust me. Okay, let's talk about your phospholipid bilayer because I'm sure you've never talked about it before. No, I know you have. You probably made things out of it for biology class. Okay, so phospholipids. Remember we're talking about lipids? Yes, so this is also, you have the little polar head and the nonpolar tail. This is super important. It makes this little bilayer. It also can make these little micelle looking things. It forms a lipid bilayer. Phospholipids, similar to soap and detergent. Oh, I know, I just said that. They have hydrophobic heads and hydrophobic tails. Phospholipids have 2 tails instead of just 1 for soap and 3 for fats. So it's all about the tails. So there's your little phospholipid bilayer. That's what it looks like. And things are coming in and out. Your fats just get to come right in, right? Because they're like, dude, I hate water too. Just let me in. And they do. They're like, oh yeah, come on in. It's all right. Water hater. Just come on in through here. Everything else has to have these globs of proteins to get things through. We'll talk about that later. This is called the fluid mosaic model. Why? The membrane is fluid. Those things are not chemically bonded to each other right there. They are not. They're just like squished together. So it's fluid, so it can move, it's squishy, it can do all kinds of great things, and it's a mosaic because it contains all this business, right? It's got all these random proteins and weirdness in it. It's like a big mosaic painting. So hence the fluid mosaic model. Because it is fluid rather than rigid, it's not easily ruptured. It's not like you can pop it because it's just squishy. It's so squishy. And the nonpolar molecules easily enter the cell through the membrane and it can move place to place. So it's awesome. Okay, so you have two types of transport, right? So now you're trying to get through this thing. So you're not a big old blob of fat, you're anything else. And you're like, how am I going to get through this blob of weirdness with the hydrophobic and the hydrophilic? Two ways. One way is there's all these really great channels, or sometimes there's just passive transport. Remember osmosis? Right, that. So that is passive transport. So that's basically osmosis diffusion. The substances just move by diffusion from a region of higher concentration to a lower concentration. You don't need ATP for that, it just does it. Like we didn't do anything to the little tube or a little sac in lab, right? It just did that. We didn't have to add energy or do anything to it or heat it up or do anything. It just did that. It just does it. It just does osmosis and diffusion. It's free, passive, passive. You don't have to do anything to it. Active. This is like, okay, we got to get these guys out. You got to go beyond the gradient, and this is not what would naturally happen. We got to move stuff around. It usually requires energy. It's a lot more complicated to draw. Okay, passive and active. These are important to know the distinguish between those two. And I have a picture. So simple diffusion is just like, dude, higher concentration here, lower concentration here, peace out. We're out. We're trying to diffuse this thing. We're trying to make everybody equal. We love equality. It's all about equality. So we're trying to just move out. Nothing has to happen free, right? It doesn't cost you anything. This is like, okay, I can't get in here because of the weird hydrophobic hydrophilic, but there's this little awesome tube that goes through here. Dude, I'll just use that. Simple diffusion. Nothing happening. Doesn't cost you anything. This is like intermediate. This is facilitated diffusion. Facilitated. What's happening here is somebody's carrying it. So it's like a sodium or something is like, hey, I'm going to go into the cell. If you want to just like come with me, that'd be awesome. Like I'm going down my concentration gradient so you can just hop a ride with me. That sometimes happens. You get a proton carrier. These things are still free. It may be linked to something else, but it's free. Then you have the active transport. This is going to cost you some ATP right here. You want to get from here to here, you got to pay up. You got to pay up, and the currency is ATP, because that's always the currency, right? Okay. Again, simple diffusion. This is in your some solids enter and leave by simple diffusion. This is just boom. You just go. It's so simple. It doesn't cost you anything. Others go by facilitated diffusion. This is a little bit more complicated. Things change shape. You got to have a co-transporter. You got to, like, somebody has to be going that way. Like, dude, hey, are you leaving the cell? Are you going in that cell? Hey, if you're going in that cell, could I just like go with you? Yeah. Facilitated. Somebody has to facilitate the relationship. It doesn't just happen on its own. Maintaining concentration gradients usually requires some kind of expenditure of energy. This usually doesn't happen for free. So even the guys that get to go for free, that's happened because somebody else has made that happen. Because somebody has set up the concentration gradient just right so it goes in and out. Usually that somebody is the sodium-potassium pump. I will say the words. I want someone to keep track. Someone who's taken physiology. I will give you extra credit starting now. Keep track of the number of times I say the word sodium-potassium pump. I'm dying to know because it's got to be at least more than 100 times, will I say, in physiology. Sodium-potassium pump. This is how your whole body works. I know it sounds crazy, but I'm not kidding. Everything works from this guy. This guy is totally amazing, and I wish I had like a whole lecture just to talk about him, but I will in physiology. This guy uses ATP, and he basically brings the potassium in, takes the sodium out, and then that thing does all kinds of amazing other stuff. Trust me. Sodium potassium pump is amazing. These guys are packaged in lipoproteins. You have this funky looking phospholipid bilayer. I only have like 30 seconds. Oh, there's no way I have time to get to this. try and write it down and just pause it because we're going to go through all this stuff in a beautiful picture in the next lecture. But just write all this stuff down now. And I promise you in the next lecture, I will make a pretty picture and explain